gentlemen, welcome to the 8th lecture in special relativity. Today we're continuing our discussion of Maxwell's first equation, which is Gauss's law of electric fields. Today we're going to be talking about, quite simply, the dot product of the electric fields with the normal vector. I want to begin with a simple do now, which asks the following questions. Number one, why don't you go ahead and set up physics here? Right. So number one, what is the electric field? Pay no attention to what I do. Just go ahead, set up your physics or whatever. What is the electric field? You can give either a visual representation or the actual mathematical answer. And next question is, what is the unit normal vector? What is n hat? Right? So go ahead, good luck. I'll give you a few seconds and don't waste your time.
Excuse me, instructor.
Yeah?
I'm about to take an online exam that I forgot yesterday, so I need headphones. But where are they?
I'll grab you some headphones.
Thanks. I don't want to annoy anybody by taking my online test.
Yeah, sure. Okay, so let's go ahead and answer these questions. What is the electric field? Let's begin with the basic answer, which is that the electric field.
You have reached a lot of people,
Thank you.
approximately 4,000.
Now, the electric field is simply a vector field that is in the same direction as the electric force, right? Which is also a vector. And its magnitude is also proportional to the electric force and inversely proportional to the test charge in consideration. Perhaps to give you a certain visual, I would say that you draw an electric field and take a look how it looks. So let's say we have some kind of a positive charge here. And of course this positive charge is going to create some electric field that emanates radially outwards. Something like that. Right? And of course these blue lines represent the electric fields lines of our positive charge. What else? Well, the electric field basically tells us that if I put some kind of a test charge here, and test charges are conventionally positive, it's gonna swing outwards in the direction the electric fields, the net electric fields on this electric charge, on this test charge, is going to be in the same direction as the electric fields. Okay? So the direction of the electric field and the electric force will be the same, and the magnitude of the electric fields on this test charge, let's call it Q2, is going to be proportional to however much charge that this Q2 carries. Okay, and what is n hat? Well, n hat, as we discussed in our previous lecture, is the following. It's a unit normal vector, right? So how can I write that down? Every vector has two things, a magnitude and a direction. So the magnitude of n hat we can denote as that, right? Looks kind of like absolute value, and that's going to be equal to 1. And the direction of n hat we can denote as dir n hat. Whoops, this should be an ending parentheses. And the direction of n hat is going to be what? Well, n hat, remember, is going to be perpendicular to whatever infinitesimally small area we're considering. So I like to write it as dir n is perpendicular to dA. So that's our do now. Hopefully that is pretty easy. Our lesson is also pretty short today. This is kind of a bite-sized lesson. And in our lesson today, we're going to be talking about what it means to take the dot product of the electric field with the unit normal vector. So let's erase all of that, and boom, we have a clean, nice board for the lesson. So to help you understand what the dot product of the electric field and the unit normal is, I want to start with the picture. So I'm going to go back to my saddle, my horse saddle, and it's going to look something like this. Okay? Now keep in mind, this is of course by no means an accurate representation, but here you go, that's my surface of interest, let's call that S. call it S. And this surface is of course in some kind of an electric field, right? So you can imagine electric field lines everywhere. It doesn't have to be uniform, it just has to be a vector. Right, so electric field lines everywhere, not just along the surface but also outside of it. Okay?
Subscribe to Bari Science Lab to fall in love with math and science, especially programming.